Again, welcome. Today is March 16th, and I was commenting earlier that it's almost a month since we started this class in the spring. So we covered a lot of material so far. We are in chapter, 10? Okay, so we covered quite a few materials in here. So we went from the ideas behind the study of motion, basically, to Newton's laws of motion. And today we're going to discover continuation of that, namely the idea of trajectories of planets and orbits and things like that. And of course, this thing was evolving by itself in astronomy. People in the old days, they were looking at the sky and they know that something is basically, they'll notice the motion of the objects in the sky. They divide them into two kinds of groups of objects. They have the, of course, ignore the moon and the sun for a moment because those are obvious big objects, okay? Some people worshipped them and they made them into gods and things like that and associated them with all kinds of mythology and things like of this nature. But there was distinctly those tiny objects in the sky, which we called stars. There is two kinds of them. There is the ones that never change their location. Albeit a year round, they change from place to place, but you come every year on the same place and you will find them in the same place. And they belong to constellations, basically. And those constellations are shapes in the sky that you can see, and you can make out something out of them, okay? Depending on the culture, depending on what they wanted to basically associate with. They have hunters, they have dogs, they have scorpions, they have all kinds of things, okay? And the point being is those objects, they don't change. However, there is different kind of classification of stars that move, okay? From location to location to location. They move actually noticeably during the week itself, let alone during the year. So those objects are moving stars, okay? So we call them traveling stars. The word planet stands for a traveling star as opposed to a star that doesn't travel. Or wandering star, wanderers, actually, that's probably a more appropriate word for them. So at that time, we were aware of at least the following stars, basically. There was the morning star or the evening star. It's the same star, we noticed. We call that Venus, actually, okay? And then there is another star that seemed to also stick to the sun. It goes either immediately after the sun or comes before the sun. That's Mercury, okay? We gave it a name. And then there were this reddish star that also moves, and it has this peculiar behavior. It goes, like everybody else, rises from the east and sets in the west, like everybody else, like the sun and everything else. Except sometimes in the week, you notice that it moves back and then continues. Sometimes in the year, it has this motion, which was called the retrograde motion, and that reddish star is actually what we call Mars, okay? So Mars has this behavior that it does like everybody else, but at some point, instead of continuing in its own journey, then it changes pattern. So we call it the retrograde motion of Mars, and that was a puzzling problem that we wanted to understand. There was another star, which was also a big star, which is Jupiter. That also was a wanderer star. And then there was another one faint there, up there. Not faint, actually bright, but the thing with it is its motion was not initially thought until we basically look up close to it. And the Babylonians and all the cultures were keeping meticulous look into these things, and they found that that also is a wanderer, Saturn, okay? That two wanderers in the sky. So basically they decided, you know what? This has some significance, all of that. They wanted to keep track, of course, for practical purposes. They wanted to know when is the next rainy season, when is the flood is going to come, and things like this of this nature. So astronomy was useful in a lot of things, okay? So when is the moon, when is kind of all of these things. It was very important for the culture, it was important for the agriculture, it was important for everything, okay? So we decided, because we have 7 objects now, we have Venus, Mercury, Mars, Jupiter, Saturn, and we also have the moon and the sun. So we decided, you know what, we're going to devise, we have 7 days also in the week. For each one of this, we have a day for it. We have the day of the sun, Sunday. We have the day of the moon, Monday. We have the day of Mars, which is Tuesday, actually. That is mardi in French, and I think there is a word corresponding in Spanish to it too. In the Latin languages, and I think also in the Germanic languages, the word Tuesday also is associated with a god that is close to or related to Mars of some sort. Then we have a day for Mercury, which is Wednesday. Then we have a day for Jupiter, which is Thursday. And then we have a day for Venus, which is Friday. Of course, we have the last day in the week, just before Sunday, the day of Saturn, Saturday, okay? At that time, we didn't know about Uranus, that also is also similar, and Neptune also has the same behavior. If we knew about them, Uranus was discovered by accident, actually, and Neptune was discovered by mathematics. Two separate, basically, astronomers using the theory of Mr. Newton, they were able to find exactly what it is. They told people, astronomers, go and look there. And sure enough, when they pointed their telescopes, they found Neptune there too. Neptune is so faint that you cannot really see it, I mean, with the naked eye. You really have to have a powerful telescope. And even Uranus also, you cannot see it with the naked eye. So those things, they needed telescopes. But if we knew about them, probably we would have 9 days in the week. Isn't that going to be fun, to have 9 days of the week, working 7 days of the week, and then 2 days off? What do you guys agree? What do you guys think? Fun or no fun?
I prefer more days off, but then it'd be nice.
Okay, so this is basically a little bit of background to this point in here, because a lot of the ideas is keeping track of orbits and objects in the sky was a problem. Of course, Copernicus first came in because everybody believed that this object can revolve around. I mean, if you and if I go outside, I think this object is moving, definitely. The Earth is sitting still and all of these objects are moving. That's what I thought, okay? Until Mr. Copernicus came in the 1500s and came up with this perspective that, look, all of these things are going around the sun, actually, not around the Earth. That seemed kind of odd. I mean, it's like, wait, how? But if you look at the data, analyze it, it's actually the sun is the center of all of these objects and they're moving around it. And then of course, that was kind of, he needed a lot of convincing, and he published his work before actually he passed away, a little before that. And then other people picked up the tab. One of them was Tycho Brahe. He wanted to really see the motion, and he documented every single one of those objects in the sky. And he saw that there is a pattern, but he couldn't really decipher it. So he hired this guy, Kepler. And Mr. Kepler's job was to actually make sense of it, but he was kind of secretive. He didn't give him all of the data because they didn't want him to take all of the credit and the recognition for whatever is discovered. He wanted his name actually to be there until he passed away, in which case Kepler had access to all of the data and sure enough came up with 3 wonderful laws, okay? So it's still the work of Tycho Brahe, is the one who collected all of that data, but Kepler, basically using his mathematical genius, he came up with an explanation for how the planets move around the sun, okay? And in that first of all, they are not going, because look, we believe that the circle is the most perfect shape there is. Earth, the reason why you see mountains and valleys and all of this mess in here is because men sinned on Earth. Therefore, Earth is kind of messed up a little bit. But if you go to the heavens, things are perfect. And there is nothing more perfect than circle. Would give us a headache with that path of Mars and why it does this thing, but that's fine. Until Mr. Kepler looked at them and said, they are actually not circles. If he looked at the data, for example, for Mars, that's the one he studied the most, they are not circles, actually, they are ellipses, number 1. And number 2, that they sweep the closer they get from the sun, because the ellipse has At some point you're close from the focal point, and at some point you're far away from it. When you're close, it's called the perihelion. When you're far, it's called the aphelion. When you're in the perihelion, you move fast. When you are far, you move slow. And that is basically the second law of Kepler. The third law took him a little bit of time, and he came up with it. And it has to do with the time it takes. He called it the law of harmony. Why some planets are closer from the sun and others are further? And that is the third law that he came up with. Then Mr. Newton came up with his theory and three laws: law of inertia, F equals to ma, and the law of basically action-reaction. And the plague hit London in the 1660s. And he was sent to home, like everybody else, from the college to the countryside. And at that time, he was given, okay, here Mr. Kepler came up with these laws. Can you make sense out of them? He took those laws and he explained them. Basically with a new thing. He found what that constant is, and then he discovered so many things with that things. People used his work to predict the return of that comet that was later on named Halley's Comet, and then later on to discover Neptune and understand everything with the exception that there's a problem. He had a problem with Mercury, and he couldn't find a solution to Mercury's problem till Mr. Einstein came along in the 1900s. Anyway, so this is in a nutshell basically where things are. So astronomy had a powerful impact on the development of science, and physics especially. Everything else, culture and naming of days and time and everything else, okay? So let's get into the topic in here, what we're covering in this case in here, at least the motion. Are you guys looking at the projectile motion? Chapter 10?
Yeah, I think so.
Okay, very good. So basically what we're going to be discussing in here is a projectile motion. Projectile motion is an example of a two-dimensional motion. It's a motion that happens in the x-axis and also in the y-axis. So it's one kind of motion in one direction, and it's a different kind of motion in the other direction. This is typical of motion in general. Motion in general can happen in 3D. You can have an object that goes left to right, up and down, in and out, okay? So that is basically a typical motion in 3D, at least in this classical mechanics, okay? Now, if you happen to throw a rock, okay, an object, is going to go and describe a parabola and fall, okay? Throw it faster, it's going to fall, but further away. If you throw it super fast, it's going to go and fall very, very far away, okay? The idea is if you throw it with just the right speed, it's going to try to fall, but it's going to go and circumvent the entire planet and come back to where it started from. So you put it in orbit in a sense, okay? That object now is orbiting the Earth. So this is what we'll talk about in terms of satellites. Obviously, if you throw it super hard, it's going not to fall in orbit, but it's going to go spiral out of the Earth. And it's going to go out completely. And that is the escape speed, the escape velocity. On Earth, it's 11.2 kilometers per second. If you want to put an object completely out of the reach of the Earth so that it leaves the Earth, you need that speed. If you want it just to stay in orbit, then you need a different speed, 8 kilometers per second. Anything less than that is going to be a projectile and falls on the Earth. So this is basically how we can understand this dynamics, okay? Satellites play a major role in our culture nowadays. You cannot leave home without them. Literally speaking, actually, they are following you everywhere. Whether you're watching your favorite sports channel or whatever, that is satellite. Whether you're calling somebody or something else, you're using a GPS system that is relayed on satellites. As a matter of fact, even telecommunications nowadays relies on satellites because of the fact that, yes, inside the cities is tower to tower, but in the middle of the oceans and the overall between the continents, it's actually satellites that are used for telecommunications, okay? I know some cables are used still underneath the oceans, but now everybody's deploying satellites. So satellites play a major role in our culture nowadays. And if they were to stop because of whatever reason it is, it's going to cause a major disruption in the everything, including the self-driving cars, including whatever you have in there. So everything is going to go haywire quickly, okay? Cause so many problems. So, and then we're going to talk about elliptical orbits. Today, you will have a task. The task is you're going to make an orbit basically for a planet, and you're going to measure its properties. Okay, so we're going to have 2 focal points, and you're going to draw the shape. Okay, you're going to do it yourself, and you're going to post the image. You're going to post the data, and I'll tell you exactly what data you need to post in here. Okay. You need to do 2 measurements. You need a ruler, like this ruler, and you need also a thumbtacks or something so that you need the string. Do not use a rubber band. No good. Okay, these things are no good. It has to be a string. Okay, and then a marker or a pen or a pencil or something like that. That's what you will need, and a piece of paper, of course, to draw these shapes. Okay, so you're going to do that, and you're going to report your data in the discussion, and then you're going to reply to at least one of your peers and comment about the eccentricity of their ellipse. In other words, how flat is it? Okay, just by looking at it and then confirming it with the calculation. Okay, so
Okay.
that.
What was the question? What was the discussion board?
Huh?
Okay. What was the
It's not-
question?
See? It's okay.
There is no question yet. Okay.
This is part of the discussion, right?
And it's part of the discussion. There is no question yet in the discussion, Brandon. Okay. It's gonna come. I'm just telling you what's gonna happen. I'm gonna show you exactly what you need to do. Okay. Sounds good?
Okay.
Okay. So if it's not clear by the end, I will clarify it. Okay. It should be easy, hopefully. Okay. It's a lot of fun, I'm hoping. Anyway, we already mentioned Kepler's laws of planetary motion and how they came out and all of these things. And energy conservation and satellite motion and the escape velocity. Okay, so again, without gravity, a tossed object follows a straight line. So if there was no object, if there was no gravity, I'm sorry, if you take any object and you throw it, there is no reason for it to go anywhere except in that direction. That is by first law of mechanics. That's the law of inertia. But gravity will cause it to bend. It's going to call it to curve, okay, and fall toward the ground. So that is basically in a nutshell what's going on. So with gravity, the same object tossed at an angle, goes on a curved path, okay? So projectile, any object that moves through the air or space under the influence of gravity continuing in motion by its own inertia, okay? There is the 2 kinds of motion. In here, there is no force. So if you throw an object, I'm neglecting friction in here, so we ignore friction. Otherwise, friction will make this distances less and less until it comes to a stop. But if there is no friction, then this object will go straight out. The separation between these 2 points should be the same, because if you take this distance and measure this distance and take any other 2 points, this one's, for example, it's the same distance as much as this one too. So this is a uniform motion. This one, it's clearly this distance is less than this distance, which is less than this one, which is less than that one, which is less than this one. So this is a uniformly accelerated motion. Uniformly because g is constant. So it's an accelerated motion. And that is because of g, which is 9.8 meter per second for every second, or roughly 10 meter per second, okay? So this is basically, you have a fall and a uniform motion, both together. They give you a projectile. Okay, they give you a projectile motion. So when the cannon is shot in here, the velocity has two velocities. It has component upward and it has a component along the horizontal direction. This does not change. This distance is at uniform motion. This will go up until it reaches the maximum height and then start falling. The combination of the two is this motion. Okay? This is the combination of the two. This is called the range of the projectile. Obviously, midway, it's half range, okay? This is the maximum height. The time it takes to go all the way from the beginning to the end is the time of flight, okay? So this is basically the properties of the motion in here. Again, the distance is in here. This distance, the vertical distances are connected by that uniformly accelerated motion, but the horizontal distances are uniform, okay? So this is a compound motion that has two components, horizontal motion and a vertical motion. One that is uniform, and the other one that is uniformly accelerated, gives you this motion. So this is what the projectile is again. So this distance and this distance and this distance are the same. However, it's clear that distance, for example, is a lot less than this distance, okay? So that is what a projectile is, okay? So this is a two-dimensional motion, and in which the horizontal component of the velocity, this quantity never changes. Whereas the vertical component starts big, gets smaller while the object is rising, vanishes in here completely, and then changes direction and starts increasing again. By the time it hits the ground, this value is the same as this value. They're equal. Okay? So this is as long as it's the same height. And here we throw it from the ground and it came back to the ground. Obviously, if you catch it in here, the velocity in here is less than the velocity in here because this is at a higher point than this one. Okay? If there was a cliff in here, this will continue falling. And then as it does, it's going to gain more and more velocity, okay? So this is again a projectile. Now this is the example of the uniform. This is the example of the cliff that I was talking about. In a sense, it's still uniform in the horizontal direction, but the vertical direction, the distances are getting bigger and bigger. Obviously, this velocity will be tremendous in here because of the fact that it gains more and more velocity. Remember the acceleration g, which is almost 10 meters per second, is how much velocity you will gain over time, every second, or lose too. Because while the object is going upward, it's losing velocity at that rate. For every second, it drops by 10 meters per second. For every second afterwards, it drops also 10 meters per second until you lose completely all of the velocity. Then it reverses the object and starts gaining it in the opposite direction. For every second, it gains 10 meters per second for that second, and so on and so forth. So this is basically the object. However, in this direction, there is no force, so it's not going to gain or lose velocity, so it stays the same. That's why this black one in here is still the same velocity. That's why we call this motion a uniform motion in the horizontal direction, whereas in the vertical direction, it's uniformly accelerated. The word accelerated is taken in algebraic sense, in a sense that when you lose velocity, you're also accelerating with a negative velocity, with a negative acceleration, I'm sorry. Okay, so the word accelerated is really in the algebraic sense. Like when you are going up, you really are not accelerating, you're decelerating, you're slowing down. When you're coming down, you are indeed accelerating, you're gaining more and more velocity. The object, when it reaches the mid-air, it's not going to stay there. It's going to start to accelerate downward. Okay, so that is the word. When I said accelerating, it has to be taken in the algebraic sense, meaning it can be positive or negative. So while you're going up, the velocity is upward, the acceleration is downward. So it's going to make this one less and less until you vanish. But when you are coming down, the velocity is down and the acceleration is down. So it's going to make it bigger and bigger. The acceleration is always pointing towards the Earth. It never changes. It's the velocity that changes. So again, this is the example of that. So this is, oops, what happened? That's the uniform motion. Obviously, this is the law that we're using in here, okay, for how much it drops. After the first second, it's going to be 5 times 1 second squared, which is 5, because 1 squared is 1. After 2 seconds, it's going to be 5 times 2 seconds squared, which is going to be what? 2 squared is 4 times 5, that is 20 meters. After 3 seconds, it's going to be 5 times 2 to the power, 3 to the power 2 still, 3 squared. 3 squared is 9. 9 times 5 is 45, okay? After 10 seconds, for example, it's going to be 5 times 10 seconds squared. This is 100. 10 times 10 is 100. Times 5 is 500 meters. Wow, after 10 seconds, it started with 5 meters. After 10 seconds, 500 meters. It's half a kilometer already, almost half a mile. 5 stadia, 5 stadium and another stadium and another football fields, I'm sorry. 5 football fields length after 10 seconds. 10 seconds is not much if you think about it. The object reaches 5 football fields, okay, because each field is roughly about 100 meters, okay? So this is basically a uniformly accelerated object in here. But this is a vertical displacement, not the horizontal. The horizontal is still at the same rate, never changes. So this distance is supposed to be equal to this distance, supposed to be equal to this distance, supposed to be, it's this one that is changing, okay? This is the one that is accelerated, uniformly accelerated. Again, this is the story with the velocities. Throw an object with a small component in the x direction, with a high component in the y direction, is going to rise more than it's going to drift to the east. Then in this case, it's going to, this curve is, of course, is going to be a parabola. This shape is a parabola, by the way. If you take a cone, 3D cone, okay, not a, and you make some cuts in it. First of all, if you come in here anywhere in the shape and you cut it in here, you're going to end up with a circle. So circle is actually a conic shape. So these are the conic shapes. So you make a circle out of this one. If you cut it at an angle, it's still a conic shape. So this is your circle. This one is actually not a circle, but rather an ellipse. If you make it right at this direction, just barely to where this one is a tangent to it, this is your parabola. Now, if you make it at wider angle in here, you're going to get a hyperbola. These are the conic shapes, 4 of them. Circle is one of them, actually. Circle is a special case of an ellipse that has the center in here. All the points on it are at the same distance from it. So if you take this distance or that distance or any distance you like, It's the same distance. So this is the radius of the circle. An ellipse, it has two focal points. The distance between these 2 points is the same. So again, this is a special case too. So the parabola is one of those cases. And that is an ellipse. I mean, that is a conic shape. So conic shapes meaning take a cone and cut it. Whichever way you cut it, you're going to end up with one of these 4 shapes, no more, no less. Okay. Obviously, you can make this one. You can make it into here, for example. You can make a line out of it. So the line, in a sense, is also a special case too, an extreme case of this too. There is connection between the complementary angles for a projectile. Projectile, if you send it at an angle, for example, of 15 degrees, this angle, this is 15 degrees, by the way, the range will be here. If you send it at 75 degrees, it's going to go all the way and come up in here. What is 15 plus 75?
90.
90 degrees. They add up to 90 degrees. If you send it at 30 degrees, this is the range. If you send it at 60 degrees, it's the same range, albeit this one is at a higher point. The 60 is a higher point than the 30, but the range is the same. Again, what is 30 plus 60?
90.
Still 90. Okay. If you send it at 10 degrees, it's going to go here, probably. Okay. So this is your 10 degrees. So if I want to bring it in here, what is the other trajectory I need to do to get it in here? What's the angle?
80.
Thank you very much. Have a nice day. So it's going to be an 80. It's going to go all the way and come back in here. So their thinking in here is 10 plus 80 is also 90 degrees. So complementary angles always have the same range, okay? Complementary angles are the ones that add up to 90 degrees, okay? Except 45 now. 45 has this range, okay? What is a complementary angle to 45? What should I add to 45 to get 90 degrees?
It's the same thing.
You add 45. So 45 is the same angle. That's the only one that is its own complementary, basically. So you can't do two of it. It's only one. So here is a question of the day. One of the questions of the day. From this picture, which one is the furthest range? Which one is the longest range? Which one do you guys see is the longest range among these things? Yeah. Which one is the furthest distance from the starting point? Which angle?
The 45 degree?
Do you guys agree with Kim?
Yep.
Yes.
Yeah, that is the longest range. So if you happen to go tomorrow to the army and they tell you, hey, come here, you're in charge of this cannon, shoot it to the enemy. I want you to get it as far as possible. I want you to do as much damage as you can so that the whatever is in it is going to explode right in the middle of their territory. So which angle should you really use then? Should you use 90-degree angle? Shoot it up, straight up in the sky? Is that a good idea to do it?
No, because then it's gonna come straight back down. We don't want that.
You don't want to do that, do you? Unless you have some ideas in your head, which probably you're going to be prosecuted for it if you survive it. Don't do that. So which angle you need to do?
Probably 45.
45, okay? So don't shoot it back too. That's going to be even more disastrous, okay? So shoot it straight to the enemy at an angle of 45. That is going to lend the furthest to make the biggest damage. So this is really the angle. In practicality, because of the air resistance and the humidity in the air, the actual angle is a lot closer to 40 degrees, okay? So when you are actually go do this, it's part of your training and all of that, they tell you about it. It's about 39 degrees, okay? because of other factors, okay? That is really why it's a little less than that. Other than that, theory says it's 45 degrees. It looks like it is, okay? So the maximum range, so this is an item of today, okay? So you really need to remember this item. So for a projectile, the longest range can be achieved with 45 degrees. Make sense? For a projectile, the longest or the furthest range or the biggest range you can have is with an angle of 45 degrees. Good. Make sense?
Yep.
Okay, so different distances. So 45 that occurs for maximum range occurs for ideal launch at 45 degrees. With air resistance, the maximum range occurs of baseball at less than 45 degrees above the horizontal. So now for a baseball, it's different because it has a different geometry. With air resistance, the maximum range for a golf ball is 38 degrees. For a cannon is about 39 degrees. So depending on the objects and so on and so forth, okay? So again, if you're going to have military training, they might tell you, okay, this is the secret. Don't tell it to anybody else, okay? So if you have that, they will tell you this is the angle for this specific cannon. This is another angle for another cannon and so on and so forth, because they have them tested and they know exactly which one is the longest range. Okay, that depends also on the geometry of the actual projectile. Anyway, so without air resistance, the time for a projectile to reach the maximum height is the same time for it to return. So without, because it's symmetrical, there is perfect symmetry in here. So if it takes, for example, how many? 1, 2, 3, 4 seconds. This is the 4th second, by the way. This is 1, 2, 3, 3.5 seconds, I should say, because midway in here is 3.5 seconds, okay? Oh, actually, it's a full second. It's a full second, I'm sorry. This is a whole second. To go from 10 meter seconds to 0, you need 1 second. To go from 40 to 30, you need 1 second. Remember, the acceleration is 10 meters per second. In this case, it's a deceleration. So this is actually 1 full second. This is actually 1 full second. This is actually another full second. And this too is a full second, albeit it slowed down drastically in this case, okay? And on the way back, it needs 1 second to go from 0 to 10. From 10 to 20, it needs another second, I'm sorry. From 20 to 30, it needs another second. And finally, from 30 to 40, it needs another second. So how many seconds? 1, 2, 3, 4 seconds up. It's 4 seconds down, because it's perfectly symmetrical. Now with air resistance, things change a little. Okay, it's gonna take more time to go up, but less time to come in. Not less than this, of course. This is the ideal situation. Or is it the other way? It's the other way around, I'm sorry. Okay. So the velocity of a typical object can be represented by vertical, assuming negligible air resistance, the horizontal components of the path of the projectile increases. The horizontal never changes. So whenever you see this word in here, you know it doesn't change. The horizontal velocity along the projectile remains the same, okay? So the acceleration is always g. So neglecting air is air drag, a ball tossed at an angle of 30 degrees with the horizontal will go as far downrange as that is tossed at 60 degrees, because they add up exactly at 90, okay? They're complementary angles. Again, satellite motion is an example of a high-speed projectile, no more, no less, okay? Except that this speed is so high that the object stay in orbit. It's trying to fall, actually. It's falling, but it's catching itself while it's falling, that's all, okay? A satellite is simply a projectile that falls around the Earth rather than into it. So it's still falling, and because it's the rate at which it's falling is the same rate at which it's moving forward, so it's always catching itself while it's falling. So now it's in orbit, basically, okay? So if you throw it super fast, first of all, this is the example I said earlier. So if you throw it with a low velocity, it's going to fall immediately. So the distance is 5 meters. So if you throw it again with a higher velocity, the 5 meters, you still have a little bit leeway, so on and so forth, until you reach a point where the object is falling, but it has so high speed that it's going to come around. So don't stick around too long, okay? Otherwise it's gonna hit you in the head. Obviously, it's very hard to do on the ground because of the air resistance and other issues. But on depending on the orbit, you can make that object to stay in orbit, okay? So this is used for all kinds of things. This is first of all the, what is it? The space shuttle. This is around 100, 200, 300 kilometers, basically. Usually that's when they have their missions. However, if you want to do a GPS, you really have to have very, very high positions for it, because for a GPS system to work correctly, you have to have it, if this is the equator, you have to have it at a distance so that it stays in its place all the time. So if the Earth is spinning, and it is, okay, this satellite needs to spin with it in sync, so that if you have your device pointing to it, it stays pointing to it, because the Earth is spinning, your device needs to stay always in sync with it. So this is the geocentric, what is it? Geosynchronous satellites, okay? The GPS systems, okay? Global geosynchronous, I lost the word for it, okay? GPS, basically. Synchronized motion, in other words. So as long as the period of revolution of this object is exactly 24 hours, just like the Earth is, then you will see them in their location all the time. So that's why they are used for television. For that, they need to be very far away from the Earth. The distance usually around 30-something thousand kilometers from the Earth, okay? So the object, this object, they move in a circular paths, and the period of the object is for satellites close to the Earth about 90 minutes, for satellites higher up, the longer periods. So you don't want them to go around the Earth in 90 minutes, because then they go too fast. You don't want them to be too slow. There is only one location in the distance from the Earth where this works, okay? Where the period is exactly 24 hours. It's not very hard to compute, actually, but this is the idea with it. Okay, if you give an object an 8 kilometers per second of speed, it's always going to catch itself. So the horizon drops by 5 meters, so it's going to be just stay above the horizon. And this is basically the speed with which a satellite minimum need to have in order for it to stay in orbit, okay? So if you give it that speed, it's going to always stay at least in that height. So it's gonna fall 5 meters, but it's going to move away so that the new height now is still 5 meters. So the stays 5 meters above the horizon if it's on the ground or wherever it is, okay? So this is the speed with which to put an object into orbit. So this is a question, probably you're gonna have it in the quizzes and so on and so forth. So make sure you're paying attention to it, okay? So what is the question here? So when you toss a projectile sideways to curves as it falls, it will be on Earth satellites if the curve it makes matches the curved surface of the Earth, results in a straight line spiral out of, and definitely, now it's going to go in. What am I looking at? What is the question? Is this one? Yes, this one. It has to match the Earth curvature, okay? So that's if it drops, it's supposed to drop 5 meters, so it has to travel far enough so to catch that 5 meters, basically. That is what the 8 kilometers basically tangent comes in, and that is what the 8 kilometers per second is, because in 1 second it's going to drop for 5 meters, okay? So when a satellite travels at constant speed, the shape of its path is a circle, because a circle has an acceleration that is v squared over r, and this velocity is constant in magnitude. So the speed is constant in magnitude. Then the the direction is changing, okay? The radius in this case is the same. So the curvature in this case stays the same all the time. If the object accelerates, then in this case, it's going to go on a wider curve. If this decelerates, it's going to come closer. So as long as it keeps this velocity, it should stay in its orbit with that same speed. So a payload into orbit requires control over direction of the object and the speed of the rocket. So you really have to give it just high enough speed so that it reaches that point and then gain that speed in there, okay, of 8 kilometers per second. So that's why you adjust its speed while it's mid-flight. Here is your task of the day. Let me switch cameras, show you what I did and how you're going to do it yourselves, okay? To build your own ellipse. It's exactly this image, okay? So let me switch cameras. Let me stop sharing the screen first and share with you. Hopefully the camera is good enough right now. I didn't test this camera today, so hopefully it's working. What is the camera? Video. Okay. Of course, you don't see anything because they have that thing there going. So let me remove the background. And none. You guys see my drawing?
Yeah. we can see.
Okay, very good. So basically what I did was, what is the rest of the stuff that I used for this one in here? So I have a ruler in here, as you can see, okay? And I have a marker that I've used for that. Here is the marker. And I had a string. Here is the string, okay? So basically, the string has to be slightly longer than this distance, okay? Don't make it too tight, okay? It's gonna have you're gonna have a lot of problems with it. The string needs to be free to move around both of this, okay? You cannot have it tied in here. If it's tied, you're gonna have difficulty with it. So it needs to be freely moving around this objects in here. So when you are doing this, when you're drawing it with a marker or a pen or pencil, it took me a couple of tries actually. As you can see, this jagged in here because you probably don't see it because of the fact that it is not showing, okay? Because as I was running the marker in here, at some point this end gets stuck in it, okay? So it gave me this not so good thing. So the first task is you draw. Brandon, are you here still? Good. So this is the question that you asked about earlier, okay? So is to draw the ellipse. Okay, so this is one way of doing it, basically. Make sure that you have a string, two fixed in here. It took me a little bit of hard time to get this. I broke a couple of them to have them in there, okay? But it worked, okay? Then after you do that, after you have a good one going for you, this distance, like I said, needs to be slightly bigger, but not too big, because if it's too big, if you make the string too big, then it's going to be outside of the paper. You don't want that too, so you have to make your case for it. I drew it accordingly. I called this one the sun, okay? And this one is just another focal point. This point is not needed at all, this one. The sun is located in one focal point for all of the planets, basically. Practically, this is called the focal point or focus. This is another focal point or focus, okay? This word was invented by Kepler, actually, okay? Both of them are called foci or foci. Whichever way you say it is fine. Okay, the 2 points. So this is a characteristic of the ellipse. I want you to measure this distance from here to here in your own and call it C. So you're going to report the value of C. Use centimeter ruler and measure that distance. For mine, for example, that distance is, I would say, it's not exactly 9. It's not exactly 8.5. I would say it's probably 8.7. Okay, that's a good enough rough number. So I'm gonna write 8.7 centimeters. Okay, that is my measurement for C. Okay. I also need the measurement for A. This is the aphelion. This is the perihelion. Okay, probably I'm not saying the H correctly because of the fact that maybe I need to sound it more. Anyway, you need to measure this distance from end to end. For my case, I'm gonna be happy by saying it's 17 centimeters, okay? So this number for me, A is 17 centimeters, okay? I also need to measure this distance. This is called B now, from end to end. This distance, right? Middle, smack in the middle between this distance and that distance. So if it was 8.7, divide that by half roughly and come in the middle in here and mark that point and then draw this perpendicular in here and measure this distance again. So I'm gonna call this distance 14.5. So this distance is 14.5 centimeters. That is your first task. You're not doing anything outside of this. So your first job is to just draw the ellipse. For my case, this is where the sun is. This is the closest point where we are in the sun. This is the furthest point where we are in the sun. This is the equinox. This is the other equinox. The aphelion in here is the winter solstice. Solstice. And this is the summer solstice. Solstice. Right now, we are going from winter towards spring. We are in March. We are close from this period. The Earth is somewhere in here now, okay? So this is where the Earth is. You don't need to mark this, okay? All you need is, again, to draw your ellipse, report A, B, and C. That's all. Give me the values of A and B and C. A is the major axis. B is the minor axis. C is the distance between the two focal points, okay? You need A, the major axis. That is one thing. You need the minor axis. That is B. And you need the distance between the focal points. The foci or foci distance, which is C. So that is what you need to do, okay? So if you're confused, this is item 1 and item 2. That's all you're supposed to do, okay? However, I'm telling you right now a little bit more information. This is where we are on March 20th. Is it March? Yeah. March. We're going to be in, going from basically through this point in here, okay? The equinox. The days and the nights will be the same, and then we'll be moving to the summer, and then we come back to the fall equinox, which is around September. So this is going to be around June 20th or June 21st. This is around September 21st, and now we're back to December 21st. Okay, so in December we're in here. Obviously, this is exaggerated big time, but that's the case. Exaggerates in terms of the distance between the focal points for the Earth, okay? And this is similar to Mars and similar to all of the planets. Do you guys understand what you're doing, yes or no?
Yeah.
Okay.
Did you have a way for us to determine the original, like the C?
What do you mean the C? No, you're choosing.
Okay.
Whatever works for you, okay? This is be creative, basically. It's your task now. It's your thing, okay? So it's your job now, okay? You're designing this, so you have to make your best, basically, drawing with it. Again, what I need from you is this distance, the furthest distance, which is called the major axis, the closest distance, which is called the minor axis, and C. In the discussion, there is instructions for how to reply to your peers, okay? This looks kind of almost like a circle, but it's not quite right, okay? So in your replies, what you're gonna do is you're gonna take a calculator or small device, doesn't matter which, okay? Do I have a charge in this one? And divide C by A. So I'm gonna divide C, which is 8.7, divided by 17, okay? If you use centimeter in here, use centimeter everywhere, okay? And try to stick to the centimeter, okay? It's 0.511. For me, the eccentricity of this one is 0.511. It looks, if it is 0 or very close from 0, it's a circle. When these 2 points are very close from one another, it becomes a circle. When these two close are stretched as much as this one, it looks like it's a line, actually, okay? So it's going to be very, 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 trying to draw very, very, very with my hand, okay? Very narrow, okay? So it's going to be a thin ellipse. In that case, when C is very close from A, as a matter of fact, the ratio you're supposed to calculate is C over A. If this number is 0, very small, then it's in a circle. If this number is almost 1, meaning that this distance and that distance are the same, then in this case, your ellipse is flat, basically flattened ellipse, okay? Most of the planets, their values are very close from 0, even that of Mars, okay? Pluto is not. Pluto is odd, actually. Pluto and some other objects in there, like Halley's Comet, it's very, very, very basically like this for a comet. That's why it takes 76 years before it comes back toward us in here, okay? So again, you guys understand the task, what you're supposed to be doing for this one, yes or no? Because I'm going to go back to the other camera. Good?
Yep.
Okay. So let me choose my fancy Mars background and change the camera back to this camera. Okay, so let's continue now with the other one. So again, that is what you're supposed to be drawing. I was already talking about this one. Let me remove this camera now out of the way. So again, when you throw it with a high enough velocity, it's going to go through this elliptical path. So an ellipse, which is another conic shape, by the way, there are 4 of them. And this is actually where the planets are orbiting, okay? People made a big criticism to Mr. Kepler when he came up with this idea. Well, you can't, ellipses are no good. It has to be a circle because circles are more perfect. And then there was also criticism with the fact that you guys are nonsense. There is no such a thing. Everything revolves around the Earth. Mr. Galileo in 1609, the same year actually when Mr. Kepler came up with the first 2 laws, including this one about the path of the object, he actually looked at Jupiter and he saw it has, the first night he saw 3 moons. He saw Ganymede, he saw Callisto, and he saw Europa. The next night he saw the 4th moon for Jupiter, and that is Io. And here you have an object other than the Earth that has 4 objects revolving around itself. So it's not true that everything revolves around the Earth. So it was a big confirmation of Mr. Galileo has done that time. So the thing with it is, it was a major, major revolution during that time. So again, these are the Kepler laws. So Kepler was assisted to the famous astronomer Brahe, who directed the world's first observatory. Tycho Brahe was the last basically astronomer not to use a telescope. Nowadays, all astronomers use a telescope. I have one at home in here, which is about 5-inch telescope. I used to have a much bigger than one, but keep on moving. I basically get rid of it because it was too bulky. This one is nice. Okay, the one I have right now, it's kind of small and mobile and things like that. It costs only $200, which is really not bad at all for a telescope. You can buy it from Astronomers Without Borders for that much. It's a really nice telescope. Okay. So anyway, he used data his mentor Brahe had collected on planetary motion to figure out. He found that the motion of the planets was not circular, rather it was elliptical. That was the first law. The second law basically was that the area swept by this line, which is an imaginary line between the sun and the planets at different points in time, is constant, meaning if it takes a week to go from C to D, it took also a week to go from B to A. And that is actually kind of the reason why it does this one is because it's moving faster in here to cover this much ground on the orbit. But the area itself, the shaded area, is the same as that area. The third law is the one that is basically relates both the time squared and this half, basically, that A, which is called the semi-major axe, cubed, and that ratio he found it to be constant. It took him from 1609 to about 16 or about 8 years, 7 years or 8 years after that to publish, to come up with the third law. But these are his 3 laws. Okay. So again, Mr. Newton came in later on and he gave a beautiful explanation based on his laws of motion and to why this is. Okay. So the energy, recall the object in motion has a kinetic energy. So the reason why an object will leave the orbit is because if you give it a high enough, basically kinetic energy, then it ultimately can leave. Okay, it can leave with no energy whatsoever. If the kinetic energy and the potential energy, they cancel. But if it has more kinetic energy, it's ultimately going to go in outside of the orbit. Okay. Again, this is the conservation of energy. It's only kinetic and potential in this case. So when we are very close from here, we have a high kinetic energy. When we're very far, the distance is super far, we have a lot of potential energy. So the kinetic energy is less. So that's why the velocity is higher in here, because you have a higher kinetic energy, less potential energy, and vice versa in here. So this is basically Newton's explanation for it. Actually, as a matter of fact, it has to do with the angular momentum, because there was an odd thing too. All the planets seem to be orbiting on the same plane. And that can be only explained by another thing, which is the conservation of angular momentum. So when satellites gain altitude and moves against gravitational force, its speed KE decreases, and its speed and potential and kinetic energy decrease. Both of them, they decrease, and decrease what is this? And decrease continues to the apogee. In general, the word apogee is used for the Earth, and the case for the Sun is aphelion. Okay. And it's vice versa for the case when they are closer from one another. So the escape velocity, this is what Pioneer 10 was launched in 1972, and it was directed toward Jupiter. And basically, we have sent so many probes. The last one was Perseverance, and we had to use the escape velocity. The escape velocity for Earth is 11.2 kilometers per second. Where is my marker? So for Earth, it's 11.2 kilometers per second. This is how much speed you need to escape the pole of the Earth. For Mars, it's a lot less. So Mr. Damon, when he was stuck on planet Mars, he needed not that much escape velocity to exit that planet. Now, this is in a nutshell. Okay. So we sent so many probes using that aspect in here. Since we're talking about the escape velocity, it turns out that the escape velocity is a property basically that has to do with the mass and the radius of the planet. For an object to leave the entire sun from this location, it needs a higher escape velocity. So those Voyager and the other probes that are leaving the solar system, they gain tremendous velocity actually when they orbited through, when they basically went through Jupiter and other planets. So that's why now they're actually in the outskirts of the solar system. So anyway, this is basically in a nutshell the chapter. So you remember your task, what you're supposed to be doing. If you're not sure about the calculation, please go to the discussion. It gives you exactly what you're supposed to be doing in terms of the ratio in your replies to other classmates. Do not report on your E. This value is called, I'm sorry, I'm not even sharing this thing. Really. This value, what is it? This value in here, that is called E. Do not calculate your E. Somebody else will, okay? Make sense? Somebody else will actually reply to your thing. Are we good?
Yep, sounds good.
Okay. I'll see you guys Thursday, same time. And if you have any questions, please let me know about this task or anything else. And hopefully we'll answer it. Okay. Let me stop the recording first.